Hello there. In this video, I want to talk about binomial expansion. I want to talk about what it is. I want to talk about why we use it and how does it relate to the previous video of Pascal's triangle. Okay. So the first thing I'm going to do is I'm just going to start off by giving you the formula. Okay. So this would be if I have a binomial of two different terms, either added or subtracted. The general form is usually given as an addition, and we can make adjustments with subtraction. So a binomial term of, in this case, a plus b to the power of a power n. And keep in mind, n would be a positive integer, okay? So this formula is n choose 0 times a to the n. Actually, I'm going to put that on the outside. It makes more sense to do it that way. A to the n times b to the 0, okay, plus n choose 1 times a to the n minus 1 to the b to the 1 plus, and I'll continue down here, and I'll do dot, 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 plus n choose n minus 1 times a to the power of 1 times b to the power of n minus 1. Let's see if I can squeeze in this last term. Plus n choose n times a to the power of 0 times b to the power of n. Okay, really quickly, let's notice the pattern of what's going on in this binomial expansion. Okay, we start with n choose 0. Okay, so that was the purpose of going over combinations. To understand binomial expansion, we need to understand combinations, at least how we get it. N choose 1, n choose, and then all the way till we get to n choose n minus 1, and then n choose n. So the combinations are increasing, and we'll go through. So if you had 3, you do 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3, all the way up. So the R of the combinations formula is increasing by 1. The A term starts off as a to the n, then goes to a to the n minus 1, so it decreases in 1 all the way till we get to the end of a to the 1, a to the 0. Okay, so the A term, the first term in the binomial, starts off with an exponent of n and then decreases in 1 every time. And then we've got the B term, does the opposite. We start off with a power of 0 and increases in 1 until we get to the end, and the a and n exponents have effectively switched, okay, from the beginning. So this B term starts off at 0 and increases its exponents by 1. A couple things to note. Notice the R in the choose formula is always the same as the exponent of the second term, okay? Another thing to notice is that no matter where you're at in the binomial expansion, the exponents should always add to the n, to be the original exponent, okay? So even n minus 1 plus 1. So n minus 1 plus 1, well, the 1s will cancel and I get n. That should always be the case. And here I've got 1 plus n minus 1. Once again, the 1s cancel and I get n, okay? So that should also be the case. So this is the binomial expansion. So the question is, why do we use this? This looks like a big, long, complicated formula. Formulas are supposed to make our lives easier. Why does this make our lives easier? So to discuss that, let's go over a couple examples, and let's go over them how I've done in previous videos. So we have the quantity here, 2x plus 3. So this is a binomial of two terms that we can't combine. So 2x plus 3. Remember that when I'm squaring something, it effectively means I'm multiplying by itself. So 2x plus 3 times 2x plus 3. And in the past, what I would do is I'd set up my table, 2x and 3, and then 2x and 3. And so then we go through, we get 2 times 2 is 4, and then x times x is x squared. 2 times 3 is 6, that's x, and 3 times 2 is 6x, and then 3 times 3 is 9, and my diagonal adds together to give me 12x. So my final answer is 4x squared plus 12x plus 9. Now, I think this is a perfectly acceptable way of doing this. Yeah, I mean, you don't have to use binomial expansion for a problem like this. In fact, you probably wouldn't because it's too tedious for such a small example. So let's up it one. So I've got the same binomial, 2x plus 3, now to the power of 3. So understanding what we know about exponents, this would be 2x plus 3 times 2x plus 3 times 2x plus 3. So something multiplied by itself 3 times. Now, to do the area table, you would have to do the area table for 2 terms, find out what that is, which we have that. It's not a mistake that these bases ended up being the same. So this is 4x squared plus 12x plus 9. And then times 2x plus 3. Okay? And then we would have to do an area table for this. So let's try that out. Let's do 4x squared, 12x, and then 9. Now we've got 3 terms along the top, and then 2x, and then 3. So I've got 2 times 4, which is 8, x cubed. 2 times 12 is 24, and that's x squared. And then 2 times 9 is 18x. 3 times 4 is 12x squared. And then 3 times 12 is 36x. And then 3 times 9 is 27. And then, again, we've got the diagonals. Okay, so we got 8x cubed. We have got 12 plus 24 is 36x squared. We've got 36 plus 18, that would be 54. And then we've got plus 27. So, I mean, if we didn't have this original table to begin with, then we would have to do 2 tables to do to the power of 3. And even 2 to the power of 4 wouldn't be that bad because we'd have 2 of this polynomial right here, 4x squared plus 12x plus 9. So you still only need to do 2 area tables. But then you start thinking, like, but now we're getting into, like, exponent of 5, 6, 7, 8. How many area tables am I going to have to create for that? That is why the binomial formula exists, or the binomial expansion formula exists. So let's go back to that formula really quickly. And let's talk about where Pascal's triangle comes in. These combinations are the rows of the nth, or is the nth row of Pascal's triangle. So if you don't even have to memorize Pascal's triangle, you just have to memorize how it's set up. So remember, it starts with a 1 at the top, then 2 1s, and then remember that 1s are going on the outside. And then to get the middle terms, we add the 2 previous edge terms together. So 1 and 1, and then we add these together to get 3, add these together to get 3, and then 1, and then that gives us 4, 6, 4, and then 1, and so on and so forth. So how many rows would you do? Well, you'd only do to the row that you need, okay? And after a while, you may even think, oh, I just know that row off the top of my head. The more you get familiar with this, the more you will memorize it, but it's not necessary. So let's take a look at what an example would look like. So I've got the binomial of x plus y to the power of 4, and I've got my Pascal's triangle already set up to the 4th row. Okay. So this would start off with n choose 0. Well, n choose 0 is just this entry right here. So that's just 1. So I'm just going to write a 1. I'm not going to write 4 choose 0. Okay. Times my a term. Well, let's note really quickly what my a term is. My first term is x. So I'm writing x, and remember this term gets the power of whatever is initially in this exponent. So that's x to the power of 4. And then b from the initial formula would be y. And this always starts off with a power of 0. Now, before we go any further, do these exponents add to the original exponent of 4, and they do. So we're good so far. All right, so I'm going to put a plus sign. And always when I'm working out these terms, I always start with a plus sign, and then if I need to simplify it along the way and change it to a negative, that will come out, but that'll be in a future example. So the next term in Pascal's triangle is I'm going to go to the 4. So 4 choose 1 would be 4. So I'll just write the 4 times. And now remember, I'm repeating this term right here, but with one less exponent. So that would be x to the power 3. And then I'm repeating this term here, but with one more in the exponent. So that'd be y to the power of 1. Okay. Once again, we'll do our check. 3 plus 1 equals 4. So we're good. Let's go ahead and do one more term up top, and then I'll start a second row. So we've got the next term in Pascal's triangle is 6. 6. And now, again, x, but with one less power, so x squared. And then y with one more power, y squared. All right. Really quickly, I don't think I explained, why do I need the fourth row of Pascal's triangle? Because this is 4. If it was 3, you'd use the third row. If it was a billion, you'd use the billionth row. All right, so our next term in Pascal's triangle is 4. Again, this term with one less exponent, so that'd be x to the power of 1. And then we've got this term with one more, so y cubed plus, and then our final term in Pascal's triangle is the 1. This term with one less exponent, so 0. And then this term with one more is y to the 4th. And again, we stop checking our exponents, but 2 plus 2 is 4, 1 plus 3 is 4, and 0 plus 4 is 4. So great. Okay, and notice our final check that we did this right. This is just the reverse of this, and that's the end result of what you should get. Okay. Well, we just have to multiply everything together, so I'm going to start my equal sign over here. So 1, notice y, and remember, anything to the power of 0 is 1. And we're going to assume that neither of these are 0, because then it wouldn't be a binomial anymore. It'd just be something plus 0, which is itself. So I'm just going to get rid of that, and I'm going to get rid of that. So 1 times x to the 4th, that's just x to the 4th. Okay? Here, there's nothing really to simplify. This is just 4x cubed. And we don't have to write y to the first. We can just write y. And then there's nothing to simplify again. 6x squared y squared plus 4x y cubed. And then y to the 4th. Yeah, there wasn't any major calculations to do there. We are just making sure it looks nice and tidy. And so then this is our final answer. All right, so another example. Let's look at one with a minus sign. So I don't have my Pascal's triangle. Let's get that set up. 1, 1, 1, 2, 1, 1, 3, 3, 1. All right, so I need the third row, so I'm going to stop there. All right. I notice that a is equal to x, and for now I'll write b is equal to a negative 1. So remember, the binomial formula initially starts with a plus b. We got the minus, so we'll acknowledge that as a plus a negative. Okay. So we start with our 1 times this first term to this power, so x to the 3rd, times, and now this is why I put them in parentheses in the initial formula. We're going to put negative 1 to the power of 0. Okay, so then we're going to look at the next term, put the plus, 3, this term with one less power, x squared, and then this term with one more power, so negative 1 to the 1st, plus. All right, next term in the binomial formula, 3. Well, actually, sorry, I don't need the parenthesis. We've got x, and then, so this term with one less power, and then this term with one more power, so negative 1 squared, plus this term, which is just 1, times x, this term with one less power, so 0, times this term with one more power, negative 1 cubed. To make my job a little bit easier when I'm simplifying this, I like to cross out anything that's a 1. So we can start with anything to the power of 0. So that's gone. That's gone. Let's not even look at it. And then let's just cross this off. Because again, anything times 1 is itself. So just having it out there is just extra detail that we don't need. So this first term, when I write out my final answer, is just x cubed. Now, something interesting happens. We get 3, and this time, since this is a number, we actually have a computation to do. -1 to the first power is just -1. Well, we'll do 3 times -1, which is -3, but because that's a negative, we will change this to a minus. So I'm going to say -3, and then we've got our x squared term. And then, okay, maybe I have a minus again, but I've got -1 squared, which is just a +1. So that actually can get crossed off. So when I say cross off anything that is basically 1, so anything to the power of 0, any of the binomial coefficients that are 1, which being the first and the last, and then anything that's 1 or -1, specifically -1 to an even power. If it's odd power, then it'll come out to be -1. So this is just 3x. And then finally, we've got this computation to do, which is -1. This is why I say when it's -1 to an odd power, we don't want to cross it off because we get that negative sign and we need to bring that out front to write our final answer. Now notice something here. When this sign right here is a negative, we get alternating positives and negatives. Now x cubed doesn't have a plus sign, but it is positive, and we got a plus here. And in between those and at the end, we have the negatives. So this kind of leads us with another pattern we can follow, is if that middle sign in the initial binomial is minus, you alternate your signs minus, positive, okay? So let's talk about our last example, and we're going to relate this back to the problem that we opened the video with, the 2x plus 3, but I changed it to minus, so that we can get more practice with the minus. Remember that if it's a minus, it'll just alternate between minuses and pluses, so we should get basically the same answer, but with alternating pluses and minuses. So again, I'll write out my Pascal's triangle. And to the third row, because this is 3. All right, so now there's some other numbers to involve ourselves with. So when I write this out, I'm going to start here, actually. I've got a is equal to 2x, and I'm going to write b is equal to 3, and you'll see that when I start writing it out, I'm actually going to initially just do the entire plus minus alternating right away. Okay, so let's start. First binomial coefficient, that's 1, times this term to this power, so 2x to the third, okay, times this term to the 0. And notice we also don't need the negative there because it's a negative to an even power. The negative cancels anyway. Okay, great. So plus, actually no, I said I'd do the alternating. So this one would be a minus, pardon me. So since I know alternating pluses or minuses come, this is a minus. Second coefficient of the binomial expansion would be 3. This to 1 less power, so that's times 2x squared, times this to an additional power, so 3 to the power of 1. And again, this would have been -3 to the first power, but we already brought the negative outside. All right, now we alternate to plus, so minus plus. All right, next binomial coefficient is 3. This to 1 less power, 2x to the first. This to 1 more power, 3 squared. And I'll make mention of it one more time. This should have been -3 to the squared, but negative times negative is a positive. And now last term, we do a minus, plus, minus. We go to our last binomial coefficient, which is 1. I'll squeeze it in there. This to 1 less power, and then this to 1 more power. 3 cubed. All right, let's go ahead and simplify. Now, the numbers are not all 1s this time, so there's going to be a little bit more work to do. All right, so note that this would be 2 cubed, okay? So we have, and let's cross off our 1s, just so make our lives simple, but that's all the ones we have. So 2 cubed would be 8, and then x cubed. All right. Here we have 2 squared. So this whole thing turns out to be 3 times 2 squared times 3, which is 3 times 4 times 3, 12, 36. So minus 36x squared. Okay, we've got 3 squared, so 3 times 2 to the first, which is just 2, times 3 squared. So this is 3 times 9 is 27, times 2 is 54x. And then here we got rid of our 1, so it's just 3 cubed. It's minus 27. Okay, so what I took the time to do was write out the problem from the beginning of the video, which was 2x plus 3 cubed. And then I wrote our last problem, 2x minus 3 cubed, because the consensus was these should be the same answer except for the alternating plus minus on the last problem. And you can go back and check the video, but I wrote them out here. You can see they are exactly the same because the idea was to check the coefficients, to see if what we did in the beginning of the video was correct. But then to also get the minus in there so we could practice our alternating plus minus. And you can see they're the same. So the question is, when do we use the binomial expansion? Well, as most things in education, you kind of have to decide for yourself. Me personally, if it's just multiplying 2 terms together, I usually just go with the area model, okay? Cubed, I may get a little bold and work through it with the area models. That's fine. Anything above cubed, I automatically revert to binomial expansion. So make sure you keep that in mind. Leave a like and subscribe if you liked this video, and leave a comment if you'd like to see any videos in the future. Other than that, I'll see you for the next video. Thanks for watching.